All right, we're starting off with a giant paragraph of information. Let's read it first. So this is our first example. Because of limited food and space, a squirrel population cannot exceed 1,000. There's something right there. Cannot exceed 1,000. Hopefully that jumps out at you. It grows at a rate proportional to the existing population and to the attainable additional population. That's also something may not be as obvious. If there were 100 squirrels 2 years ago, that should pop out at you. If there were 100 squirrels 2 years ago, and 1 year ago the population was 400 squirrels, how many squirrels are there now? All right, so the first thing that I want to mention is there are hints in this problem that tell you that this is a logistic. This problem has logistic growth. It models logistic growth. So, squirrel population cannot exceed 1,000. That's one hint, because that's our limiting factor. That's k. K is 1,000. So that's the first thing that jumps out to me. And then the second thing is that it grows at a rate proportional to the existing population and the attainable additional population. It doesn't tell us what that is, but so that's our R value at a rate proportional. Actually, it's not our R value. It grows at a rate. That's our D and DT, proportional to the existing population. We don't know what our R value is. So R, we don't know. But when it says it's proportional to the existing population, that was N. And so it would be like R times N, it's proportional to this, and it's proportional to the attainable additional population. Well, the additional population is just the limit minus, so 1,000 minus whatever population you currently have. Now you're thinking, hold on a minute, wait a minute. We could, in fact, I'm going to write it in a different way. I forgot what I was saying. I paused it for so long. But what I'm going to do is I'm going to write it in a different way, because our differential. Well, I'm just going to see. Let's see what happens. I'm going to write it in a different way. We don't know what R is. I'm going to write it just like in the last video, and then see what happens. So we know that from the last video, we can model the population, dn dt, the rate at which the population grows, by dn dt, which would be some proportionality constant times the population, and times 1 minus n over k. So I'm going to plug k in, and let's just see where it takes us from there. Now, I already know that the solution to this differential equation, if it's set up like this, would be n sub 0 times k divided by n sub 0 plus k minus n sub 0 quantity times e to the negative rt. And I don't know what r is, but I am given some values for t. I am given n sub 0, and I'm given k, so I can actually figure out what r is, and that's what I'm actually going to do. And then I'll plug in something. So it's worded a little bit, maybe a little bit different than what you're used to, but because it's talking about the past. But it says, if there were 100 squirrels 2 years ago, that is what we're going to consider as n sub 0. So when t equals 0, so that's what I'm going to write down. When t equals 0, n of t equals 100. So that means the starting n sub 0, that's going to be 100. And then it says 1 year ago, well, that would be n of 1. That it tells us the population was 400. Okay, so then I can use that and I can solve for things. And also, then at the end, when we get all these values, we can plug in and see what we get. So if I have this information, which gives me that, and this information, I'm going to use n sub 0, obviously. So n of t equals 100 times 1,000, because that's what k is, divided by 100 plus 1000 minus 100 times e to the negative r of t. So I have this, I'll simplify. Whoops, didn't mean to have that. I'll factor out 100 from the bottom and then cancel it out. And that goes away. And then I have just a simple, or a more simple equation, just this part. And now I'm going to plug in 1. And I know that n of t is 400. And then I'll just solve for r. Once I have r, then I can plug everything back into my original, which would be, I think, that, because that's the simplified version. And, yeah, then that'd be good. That'd be good. I'm going to move that over. Multiply both sides by 1 plus 9e to the negative r. Divide both sides by 400. Subtract 1 from both sides. Divide by 9. Then I will exponentiate both sides. Sorry, I mean take the log of both sides. And then I have just ln and e that goes out in front, so negative r. Use my properties of logs here. So that goes to 0, so negative r equals negative ln of 6, which means r equals ln of 6. Well, that's nice. So now I'll go back to my original simplified equation here. So there we go, and I'll plug in r. Perhaps I'll simplify it a little bit. And we have something like this. That goes away. So it just becomes 6. And there we have it. So we can now plug in stuff. Let's see what happens. I can plug in. Well, what does it ask me? Because that was a lot of work just for not even solving it. The population was for about how many squirrels are there now? So remember, we considered t being 0 2 years ago. So after 2 years, t is 2. So we'll plug in 2 to this and see what we get. So plug that in, and I'm going to just start simplifying. So I get 9 over 36. Which is just 1 over 4. I'm running out of room. I can't even scroll over anymore. I'll just move this. So that's 5 over 4, and then I'm just going to do it up here. So 1,000 over 1 times 4 over 5. And that would be 800, right? So 800 squirrels now. That's what it's saying. So I was looking at some other stuff while I was doing this. Actually, when I wrote out that one equation there, I might do another video on this with a different example, with a different way to write out your differential equation. You can use whatever you like. I feel like this is a little bit complicated, and there's a different way to do it too. But that means this is different as well. So you can use whichever one you like. It's really just plugging in stuff and noticing things from the equation. All right, that's it.